Industrial manufacturing is a highly demanding environment that requires machines capable of extreme physical force, operating at very high velocity. To understand how these machines actually achieve this, we can look to Michael P. Gruver's foundational framework on robot technology and applications. Gruver defines industrial robotics as a strict applied engineering science. It requires the synthesis of two distinct disciplines, machine tool technology and computer science. These fields are completely interdependent. You cannot write effective motion control software without first mapping the microelectronics, control theory, and mechanical design of the arm itself. Before an end effector performs a single joule of work, the physical constraints and geometry of the entire mechanism must be defined. The software running the machine is entirely subordinate to its hardware. Ultimately, a robot's programming is only as precise as its physical rigidity allows. The Selective Compliance Assembly Robotic Arm, or SCARA, is a primary example of how structural configuration dictates capability. Its distinct horizontal joint layout provides inherent structural rigidity, making it highly advantageous for precise horizontal assembly tasks. Compare that to a Cartesian configuration operating on a linear box frame XYZ axis. Because it moves along rigid linear tracks, the Cartesian structure possesses the highest mechanical advantage for reaching a point in space with the absolute minimum motion error. For applications requiring a different range of motion, engineers rely on polar and jointed arm configurations. The specific physical advantage here is superior reach. These designs allow the robot to extend its manipulator significantly beyond its own base. Other models, like the cylindrical and gantry configurations, are deployed when the process demands high load carrying capacity or the ability to reach into tight machine openings without side interference. The exact geometry an engineer selects on day one permanently locks in the system's baseline limits for rigidity, reach, and payload. Productive work requires the manipulator to navigate three-dimensional space, and that navigation is split into two divided spatial motions. The blue sections represent arm and body motions. These large mechanical links are responsible for the macro positioning of the robot within its work volume. The red sections represent the wrist motions. These smaller clustered joints are responsible for the precise orientation of the tool. Once the arm navigates and the wrist achieves the correct angle, the actual work is performed by the end effector attached to the wrist. When control engineers calculate the mathematical precision of a robot's motion, they make a strict assumption. Precision is measured exactly at the wrist end, completely ignoring any attached hand or tool. Gross arm mechanics get the system into the zone, and fine wrist mechanics orient the payload. But the baseline mathematical precision of the system is always measured naked. Understanding static geometry is only the first step. When the arm is actually commanded to move, we have to evaluate its dynamic performance. Control engineers face a strict mechanical conflict. They must balance high-speed movement against system stability, also known as damping. This first graph illustrates dynamic performance in a low damping scenario. Low damping allows the arm to move towards its programmed position incredibly fast, but it induces severe instability, shown here as overshoot and heavy oscillatory motion around the final target point. That oscillation causes immediate physical consequences. It increases wear on the mechanical joints and delays the exact moment the tool can actually begin performing its work. Now look at the second graph, charting the high damping scenario. High damping eliminates oscillatory motion, so the arm arrives smoothly and settles immediately. The physical drawback is speed. High damping makes the arm sluggish, extending the time required to reach the destination. Ultimately, software control systems simply cannot override the laws of physics. The engineer must calculate a precise compromise between response speed and damping based on the exact throughput required by the factory. You cannot engineer a system with infinite speed and infinite stability. Every robotic movement is governed by a compromised control curve. Once the dynamic motion completes and the robot actually stops at its target, performance is graded on three metrics of static precision. The first metric is spatial resolution. This is the absolute smallest spatial increment into which the robot's control system can divide its work volume. The second is accuracy. This measures the manipulator's ability to successfully land its wrist on a specific programmed point within that coordinate grid. The third is repeatability. If the robot is commanded to return to that exact same point multiple times, repeatability defines the statistical variance, or spherical radius of error, around the target. These numbers are not pulled from ideal operating conditions. They are calculated under worst-case mechanical scenarios, specifically when the arm is fully extended and physical deflection is at its highest. These definitions apply strictly to point-to-point operations, measuring the static capability of the stopped arm, rather than its ability to continuously track a moving trajectory. When you read the precision metrics on a robot's spec sheet, you are reading a statistical worst-case guarantee constrained by maximum physical extension. Geometry, dynamic damping, and static precision are not isolated variables. On the factory floor, they operate simultaneously as an interlocking system of physical constraints. An industrial manipulator is a machine strictly bound by mechanical and control compromises. Mastering these hardware limitations is mandatory. Before a programmer can design an end effector or write a line of motion trajectory code, they must account for the physical realities of the arm. Today, the industry is rapidly deploying lightweight collaborative robots, cobots, where mechanical rigidity is intentionally sacrificed to ensure human safety. As structural stiffness decreases, the burden on the software increases. The challenge for modern control theory is adapting our algorithms to maintain the exact accuracy and repeatability that heavy, rigid hardware used to guarantee.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.